This is CE 2121 Module 9. We're going to talk about control survey. So what is control survey? Control survey is a determination of the precise position of a series of stations which is distributed over an area to serve as the origin or reference to be used for checking of subsequent surveys that is used in engineering projects such as property delineation, topographic and hydrographic mapping, and then of course, construction planning and design. Under horizontal control points techniques, we have triangulation, or also known as trigonometrical survey. So triangulation is a surveying method that measures the angles in a triangle formed by three survey control points. So using trigonometry and the measured length of even just one side, the other distances in the triangle can be solved or can be calculated or identified. So this is the illustration of triangulation or trigonometrical survey. So you can see here, there are three lines that forms a series of triangles in our illustration. This has 1, 2, 3 triangles with distinct known points, measured angles, also the calculated distance and calculated positions. The angles in the triangles are measured using a theodolite, which is a device we usually use in surveying lab or surveying field. This is an instrument with a telescope connected to two rotating circles. One is horizontal and one is vertical, in order to measure the horizontal and vertical angles. Another horizontal control point technique is trilateration. They use the known speed of light, which is 299 or 792.458 kilometers per second, and the time reflection of a microwave or light wave along the measured line. This is known as electromagnetic distance measurement. Here we have the illustration of trilateration. We have calculated positions, known points, and then of course the measured distances of each of the lines. So without further ado, let's start solving for illustrative example number 1. For illustrative example number 1, in a triangulation, an eccentric station is occupied instead of the true station A. Observations then are made to true station A and to station B. The observations are as follows, tabulated. We are asked to find the azimuth of line from A going to B. So the first thing that I did was to graph or to illustrate the table shown. Let's go through it step by step. We have eccentric A starting from here. This is true A and true B. It says here that the azimuth of from eccentric A growing to true A is 158 degrees, 30 minutes, and 50 seconds. Here we started from the south, rotating 158 degrees, 30 minutes, and 50 seconds. That is eccentric A going to true A. And that has a distance of 4.5. So the next one is azimuth from eccentric A going to B. So let's start at the south, rotate 216 degrees, 43 minutes, and 20.5 seconds. So this would be eccentric A to true B, which has a distance of 18,642 meters. Okay, now we are asked to find the azimuth of this one, starting from south, of course. Now, here, this is just an illustration for us to be able to solve the problem, since 4.5 is a bit small or too small to illustrate comparing to 18,642. I also indicated some interior angles that needs to be solved for us to be able to compute the azimuth from A to B. So the first one, let's try to solve for alpha. So here, alpha can be solved using 216 degrees, 43 minutes, and 20.5 seconds. Subtract it by 158 degrees, 30 minutes, and 50 seconds. So here, in order to get the interior angle, which is this one, we have to subtract or omit this angle. So that would be equal to 58 degrees, 12 minutes, and 30.5 seconds. After solving for the interior angle alpha, I would like to solve now the distance from A to B. So here, using cosine law, I would solve for the distance from A to B, that is equal to the square root of 4.5 squared plus 18,642 squared minus 2, 4.5, and 18,642 cosine alpha. So we already solved for alpha. We can now solve for the distance AB. So that is 18,639.62966. Okay, so for each of these opposite angles, we already have its corresponding opposite side. So in order to solve for beta, we're going to use sine law. So using sine law, we have Sine beta, which is this one, the opposite side to it is 18,642. Sine alpha, the opposite side to it is our distance AB. We can already solve for distance beta, but take note, we're going to be able to come up with two answers because this is a triangle with an ambiguous case. Ambiguous case meaning we have two sides or all sides known and then one angle or SSA case. Okay, so how will we know which angle to use? Let's try to use the first angle, which is 58 degrees, 13 minutes, and 12.83 seconds. So here, we'll be able to solve the azimuth from A to B. That is 360 degrees, this whole angle, minus 21 degrees, 29 minutes, and 10 seconds. Take note, this one, I got it from the bearing of AB. This one. So the bearing of AB, I calculated it as north, 21 degrees, 29 minutes, and 10 seconds going west. So this angle, I just reflected it on this side since this is a case of opposite angles. So after subtracting this angle right here, we're going to subtract now the beta. So we'll be able to get the angle from south going to our line AB. And we got an answer of 280 degrees, 17 minutes, and 37 seconds. So the question is this correct? Let's go back to our graph. This is 280 degrees, 17 minutes, and 37 seconds. So let's go back to our graph. If we are just looking for this angle, which is tilted around this point, between our north and east quadrant, that should be up until 90, 180, and 270. But we calculated an answer of 280 degrees, 17 minutes, and 37 seconds. So this should actually be somewhere here, between the south and east quadrant. So meaning to say, in our graphical representation, our answer is incorrect. So I've indicated here that our answer is not graphically correct. How about let's try to solve using the second answer for beta, which is 121 degrees, 46 minutes, and 47.17 seconds. Okay. So instead of using the 58 degrees, I use the second value we got for beta, which is 121 degrees, 46 minutes, and 47.17 seconds. Still the same, 360 degrees, omit this angle, and then omit the angle beta, you'll be able to solve the azimuth A to B. And I got an answer of 216 degrees, 44 minutes, and 2.83 seconds. Let's try to check it using our illustration. So here, if it's 216 degrees, let's start from the south. This is 90, 180, 270. So our 216 degrees lies within 270 degrees or in between your north and east direction from A going to B. So that is our answer and solution for problem number 1.